I think you're in luck. All right, we're finally going to get started. This is CSTN 286, building energy efficiency 235. All right, let's see if we can get, now how do we get that off the screen? There we go. It is Tuesday, March 1st. We're going to get started today. We've got three main parts today we're going to talk about. We're going to just go quickly back through efficiency and talk about whole building efficiency metrics, and then we're going to start to jump into the actual whole building systems. We'll talk about whole building design and the concept of it, and today we'll get into, we'll go through what the major systems are when we talk about building systems development, and then today we'll talk about the thermal envelope. And so part of this is a little bit of catch up on some things that didn't get touched on in the first couple weeks, and then this should be chapter up through and including chapter 5 of residential energy. And next week we'll start on some of the other systems, including HVAC and occupant controls. So one thing real quick that we discussed here before class, but I've got a record on here for everybody. The quiz should be open, and it's open for multiple attempts. It's not a one-shot deal, so for those of you who haven't yet started it on Moodle, there was just a little bit of confusion that it had to all be done all at one time, but you can start it as long as you don't submit it. You don't hit final and hit your submit for your attempt. You can come back to it, because yes, it is a fairly lengthy, I think it's only 10 or 12 questions, but it's a long quiz. Some of them are pretty involved. So any other questions, just email me and we'll go from there. So these are just, we define these because we want to talk a little bit about the difference between efficiency and conservation. I had a little email string debate going on about that this week. So these are the textbook definitions of what efficiency are. We're not going to read through them, but you can take a look at them. And really the whole point is what we're trying to do is not just in the entire building itself, but in the components and the systems that we put in there. We're trying to achieve the maximum efficiency out of them. And sometimes the most efficiency we get out of them are through conservation measures, but efficiency and conservation are not the same thing. The second definition of efficiency, the ratio of useful energy to the energy supplied to it, this is relatively, when we talk about systems and we talk about components, we talk about air handlers and motors and boilers and gas furnaces. We talk about efficiency in this concept. So how much fuel and how much energy goes in to how much energy comes out. And if you remember, we talked about the different efficiency types. We'll revisit those a little bit later here too. But the example here is a gas-fired furnace. So if it's an 80% efficient furnace, all that means is that for every 100,000 BTUs of gas that goes into it, 80,000 BTUs comes out. So shut this real quick. So when we're talking about components and systems and we say it's got higher efficiency, we don't necessarily mean that it uses less energy. We mean that it produces more energy based on a percentage base than an equal model. So again, and we'll talk more about this when we get some case studies in a few weeks, but just we always want to use the highest efficiency equipment possible, but it doesn't necessarily mean because something is 90% efficient, it uses less energy. It just means that 90% of the energy it uses goes towards heat or cooling. So again, the other part of it, we talk about effective operation, and this is where we start to get into efficiency versus conservation and what really is, what really truly is the most effective and maximum efficiency in our buildings. So a couple examples we'll talk about, and just in the sort of the overarching concept of efficiency. Is it really efficient? If we have a snowmelt system on the house that's 95% efficient, just the fact that we have a snowmelt system could potentially be a waste of energy. So it doesn't matter how efficient the component is, it's the overall system's efficiencies. The same thing with some of the larger houses, and it's certainly a concept and a discussion we could spend a long time on, but a 10,000 square foot house for two people might have extremely efficient equipment in it, but is it really an efficient use of the resources? And just to revisit back to the general concepts of efficiency versus conservation, and when we talk about defining buildings, we define the buildings as building types. You can't really compare when we start to dive into doing energy modeling on new buildings and energy testing and rating on existing buildings and comparisons, and we start to look at energy metrics and trying to compare one to the other. It doesn't normalize itself to be able to compare a house to a hospital. So when we talk about energy use intensity, we're always trying to compare like buildings. So, and again, just another, and we're always trying to compare that energy use to like buildings so that we can get that per square foot footprint. Here's an example, and we'll talk about energy use intensities in just a minute, but various building types, and you can see there's a pretty dramatic difference between types of buildings into the actual energy use intensity if we're looking at the amount of energy used per square foot. Just as an example in there, you can see on the far right of the graph, we've got the typical Western new construction residential. They've got an energy use intensity that's about 47, 48. And you can see when you get into things like food service, healthcare, based on not just the heating and cooling loads, but a lot of the other parameters, they use quite a bit more energy. So it's one of the challenges when we do look at whole building systems and energy metrics is making sure that we're comparing apples to apples and we're comparing the same kind of building types. So when we are measuring whole building efficiencies, we're talking in energy use intensity and primarily energy use intensity based on the building area. So we're looking at how much energy is used per square foot, and that's usually the matrix of how we're comparing. Almost always in BTUs, and we visited, you know what a BTU is, that was, I think, chapter 1 in the book. When we start to talk about a couple of the case studies, and hopefully we'll have some information on the modeling for the new Missoula College building, you can talk about it in a couple different ways. And sometimes you'll see energy use comparisons in electric only, sometimes in natural gas only. Obviously the most effective ones are the whole building metrics where you're combining the two. And so one of the things you've got to do at this point, and this is why I know a couple folks said, gosh, it's so math heavy, why do we have to do all this math? Here's a perfect example, and as we start to, even in the simplest models, because most of the buildings we use here in western Montana use two different fuel types, we've got to know how to convert to get a reasonable method of being able to measure the building efficiency. So this is just an example, revisiting a little bit of the math that was already covered. Trying to get an energy use intensity. So this is just a comparison for an 8,000 square foot building, and you can see the annual energy use. You've got the electric use and the natural gas use, and so back to that 3412 BTUs per kilowatt hour. You can see on that first line right there, in this energy use intensity, they're converting the kilowatts to BTUs, so now we have a common unit of measure for all the energy in the building. Make sense? Pretty straightforward. It's a whole lot of BTUs for annual energy use, so we convert it to kilo BTUs so that we can work with a little bit smaller numbers, and then you can see the KBTU in that next column, the annual energy KBTU, and this example is an 8,000 square foot building. So running the math, then you can see the total electric use in KBTU per square foot, and you can see the total natural gas. So now you can get one number, and that one number can be used as the energy use intensity for that building. Now that building can be compared to another building of the same type that's a different square footage. So if you had, for example, a building that was 16,000 square feet and you had the annual energy usage for that, you can run the same math and you'd come out to that energy use intensity. Does that make sense? So just a little bit of revisiting back to efficiency versus conservation. And the kind of the example I've got in here is, again, and like I say, you can have something that's very efficient, but it may not actually be conserving energy. So if you've got a compact fluorescent light, it may be 10 times more efficient than an incandescent light, but if it's in the attic and it's on 24/7, it's not actually conserving any energy. The same thing can be said for a lot of the systems, and back to the furnace example, you can have, and this is what we'll talk about a little bit later when we talk about the whole systems approach to it, but you can have a 92% furnace and it's burning 92% of the fuel oil or the natural gas that goes into it and converting it into heat, but if it has to run 20 hours a day because you've got leaky windows and no insulation, it's not actually achieving your maximum efficiency. So another example here, based on energy use intensity, and this is how we can compare similar building types. It's not always easy to compare a 500 square foot house to a 4,000 square foot house and say which one is more efficient. But if you have the energy use, you know how much energy it uses on an annual basis, you can convert that to one common measure of energy. And so if you've got one that's the 500 square foot house is very inefficient and it's got an energy use intensity of 80, so you're at 80 kilo BTUs per square foot times 500 square feet. Annually it's using 40,000 kilo BTUs. A 4,000 square foot house at an energy use intensity of 20 is using about 80,000 BTUs. So you can do the math and you can see that the 4,000 square foot house, although it's 8 times larger than the smaller house, it's only using about twice as much energy. Pretty simple example, but hopefully that explains. Somebody asked me about the energy use intensity that was in the book. I actually threw this in there too. We talk about conservation versus efficiency, and we had discussions on this last week about the question on the quiz last week that had conservation as the least expensive form of energy. And this is where that comes from. It's a little bit of a misnomer, but the concept is the energy saved is far less expensive than any energy that we have to generate. So here's the information from that slide and where it came from. But you can see in costs for all the different types of energy, the money that gets spent on conservation gets returned at a much higher rate than any of the other efficiencies. So again, we'll talk about, and when we start getting into the weatherization and existing building improvements, we're really going to start talking about a little bit more about costs. And this is where, for larger buildings, when we're looking at commercial buildings and whole building efficiency measures, the approach isn't necessarily, and most of the time the approach isn't at all, based on strictly an energy savings. It's an energy cost savings that's the focus. And we'll talk a little bit more in the weatherization and in really looking at what are the most cost-effective improvements that we do and setting the priorities of the systems. And just further on that, there's an example. I've got two different houses. One is a 2,000 square foot house. It's all electric heat. And based on its annual electric usage, it's at 58 kilobTUs per square foot. The second house is actually a combination, which is primarily probably 85% of the residential houses here in western Montana. 56% of the total energy is natural gas, so 44% electricity. It's got a little bit higher energy use intensity. So comparatively, square foot to square foot, house B, it's a smaller house, but it is less efficient. It's got a higher energy use intensity. Now comes into play, and I think you guys talked about this with Brad a little bit, the cost of electricity versus cost of natural gas. And we're making the assumption that we're at 7 cents a kilowatt hour. 7 cents a kilowatt hour for electricity, which is actually about where we're at. It's a little higher than where we're at, and then $1.10 per therm. So based on these two houses, we've got 2,000 square feet and 1,700 square feet, and the smaller house is less efficient. If they both use the same annual energy, this is where we get into the cost part of it. So taking that into account and using the 7 cents a kilowatt hour and $1.10 per therm, take our 2,000 square foot house, it's got an EUI of 58. 58 times 2,000 square feet, 116,000 BTUs. It's all electric, and so we convert that. Remember the kilowatt hours, 3,412 BTUs. So we take those BTUs, we convert them back to kilowatt hours, and then we can get our annualized energy cost. You following me? You see now the second house, we've got a little bit more math to do. We've got an EUI of 68, and of that, 56% is natural gas, 44% electricity. So we've got to break that out. The EUI is 68, we've got 1,700 square feet, so we're at that annual energy usage of 116,000 kilobTUs. So we take 44% of that, 116,000, and then divide that by 3412, 3,412 BTUs in a kilowatt hour. So we come out to 14,000 kilowatt hours. 14,000 times 7 cents a kilowatt hour is 1,047 annually. So that's the electric use of the house.
What's the 3.412 for again?
BTUs per kilowatt hour.
Oh, okay.
We're just, remember back from the very first simple example, we were getting, when you've got the two forms of energy, we've got to convert them so they're all in one unit.
Yeah.
We're doing it the other way now. We know the energy, we know the total BTU usage. Now we've just got to split it into the two different forms. So we've got to take the electricity back to the kilowatt hours so we can price it.
Okay.
And then natural gas, we run our numbers on the natural gas. We're already in BTUs. And so we come out to $715. And why this is important is this is where you start looking at, when we start looking at energy efficiency measures, we need to be able to understand what we're paying and what we will be paying after we incorporate the energy efficiency measures. And we're not going to run a lot of these calculations when we do our actual energy improvements, but we want to be able to talk about them in the sense of what's cost effective. So for example, if we're looking at these two houses and we're called in to do energy improvements on these houses, for example, in House A, we'll keep it simple because that's all in House A, if we're going to go in and do some air sealing and some insulation and it's going to cost us $900 and it's going to save us 15,000 BTUs, it's going to reduce our energy intensity and save us $300 annually, we're going to get a payback of 3 years before those energy improvements start making money. That same house, if we're going to go in and we're going to replace all the windows in the house, and it's going to cost $10,000, it might save us 30,000 BTUs, and run the numbers and annualize that out, it may save us $500 a year, but now that's going to take us 20 years to pay back. So, and don't worry about those numbers currently. It's what we're trying to drive to when we start getting into the actual design and the weatherization of the buildings is really one of the biggest things about energy efficiency and conservation is it really also has to be cost effective. So does that all make sense? No? Yes? I said no one said no, so I'll keep plugging along. Again, a lot of things have to be factored in, and we're not going to get too far. We're going to play with ResCheck just a little bit, but not much. I don't think it's as important as some of the other things we've got to get through. But a couple other things that have to be compared when you're looking at building to building are the location and the climate, the type of use, the size, the schedule of the building. When we talk about whole building efficiency measures, can also make a big difference in energy use of the building. For example, if you've got an office building and it's in operation 5 days a week from 8 to 5 versus an educational building where you're going to have night classes and the schedule and use is going to make a big difference in the whole efficiency measures. And again, being able to normalize those and get the energy use intensity is how we can compare buildings to one another. And for example, here's an Energy IQ screenshot, but once you can normalize those and you can get the energy use intensity And you can even, with that energy use intensity and with the calculations we were just talking about, you can even compare a building in California to a building in New York. Because when you can change the rate and the cost of that energy, and you can change the climate data, you can get a similar energy use intensity. And while it's not going to be exact dollar for dollar, you can get a pretty good comparison of the overall BTU load of the building and what the operational cost is going to be. So, just a couple in whole building efficiency metrics. When we're talking about existing buildings, new and existing buildings, but existing buildings, bringing them up to code compliance is usually at least a minimum target when you're talking about weatherization and energy improvements. You can always aim for better than code. New construction, certainly we talked about code as the minimum that you need to do and not break the law. New construction for whole building efficiency goals can be set anywhere from code X number of percentage better than code, or towards net zero. So we'll take a quick break right here, and then we're going to talk about whole building design and achieving maximum efficiency, and then we'll dial down into and spend the next couple weeks dialing down into all of the different systems of whole building design and how they operate together to create maximum efficiency. So let's take a quick break, 10 minutes, and then we'll catch back up right here.
So, did you just leave that going?
What's that?
Did you just leave that going? Stop.
I finally just stopped it. This is the first time I've been able to stop it. You can speak freely now, you're not being recorded.
I guess we are.
What's that?
I guess we are.
I don't know, I've got it, I thought I had stopped.
It stopped, and then whatever you did with it, slapped it down and started.